Ever wonder why robots that look like they're mastering the world in demo videos often struggle the moment they hit a real kitchen or a warehouse? It usually comes down to a massive problem called the sim-to-real gap. For a long time, we've relied on simulations to train robots because it's faster and safer than crashing a $1,000 arm into a table. But there's a catch. Most simulations are too simple. They're like teaching someone to drive using a video game from 2005. Once they get into a real car, the lighting is different, the textures are weirder, and the physics aren't quite the same. That's where a new framework called RoboLab comes in. The goal of RoboLab isn't just to be another playground for robots, but to serve as a high-fidelity stress test for the brains of these machines, specifically those vision language action models, or VLAs. These models are designed to take in visual data and language instructions and translate them directly into motor actions. But to truly evaluate a VLA, you need more than a few static examples. You need a diverse, unpredictable environment. Instead of just asking a robot to pick up a block, RoboLab uses an automated pipeline powered by large language models to generate hundreds of unique, photorealistic scenes and tasks. We're talking about everything from empty the gray bin to put the orange measuring cup outside of the plate. To determine if a robot is actually reasoning or just memorizing patterns, the researchers broke the testing down into 3 competency axes. First, there's visual competency. This tests if the robot actually understands attributes like color, size, and semantics. For example, can it actually distinguish a lime from a lemon in varying lighting conditions? Then there's procedural competency. This focuses on the logic of the action itself. Can the robot handle multi-step sequences, like stacking objects or reorienting a tool to get a better grip? And finally, relational competency. This tests the robot's grasp of language and spatial awareness. If you say, pick up the apple and the pear, does it understand the additive nature of the command, or does it just grab one and call it a day? The results were a bit of a wake-up call. When the researchers tested some of the most advanced state-of-the-art models, the success rates were surprisingly low, some topping out around 30%. They found some fascinating failure modes, too. For example, if you give a robot a vague command like, empty the bin, it might actually try to pick up the bin itself rather than the objects inside. They also noticed a shape bias. Robots would often grab a can when they were told to grab a box, simply because they'd seen more cans in their training data. This suggests that many models are relying on statistical shortcuts, rather than true visual understanding. But here is the most exciting part. RoboLab proved that high-fidelity simulation can actually be a reliable proxy for the real world. When the researchers took the same policies and tested them on physical robots, the performance was remarkably similar to the simulation results. This means we now have a scalable, fast way to find exactly where a robot's brain is failing, whether it's a struggle with a specific camera angle or a confusion between a pumpkin and an orange, without having to spend thousands of hours in a physical lab. It's a huge step toward building robots that don't just follow a script, but actually understand the world around them. So how does this actually work under the hood? To move away from robots placing objects in stiff, artificial grids, the researchers developed a 2-stage process to create scenes that look and feel natural. It starts with semantic planning. Instead of telling the robot exactly which coordinates to hit, they use an LLM to think in terms of relationships using predicates, essentially a set of logical rules. For example, instead of a coordinate, the system might use a place-in predicate, meaning an object goes inside a bowl or cluster round, which tells the robot to scatter a few items naturally near an anchor object. But logic is one thing, physics is another. To ensure these objects don't overlap or float in midair, the system uses a physical placement solver. This is the mathematical layer that translates those logical relationships into actual 3D coordinates. It handles the complex calculations, like exactly how high a banana needs to be to sit on a plate, or how to arrange a group of apples in a bin so they don't collide. And if the first attempt fails, the system uses a feedback loop. If the solver detects a collision, it sends a diagnostic message back to the AI, saying something like, the table is too crowded, try using more containment or smaller objects. The AI then adjusts the plan and iterates until the scene is physically viable. The results of this approach are impressive. When compared to a standard baseline, this method scored significantly higher across the board in visual realism and layout correctness. Whether it was a bathroom counter or a garage workstation, the scenes weren't just functional, they were believable. The real test, however, was whether a robot could actually perform tasks in these complex environments. The researchers tested a huge variety of scenarios, from putting a banana in a bowl to organizing tools in a bin. While some of the most difficult tasks remain a challenge, the system showed a massive leap in success rates compared to other models. It proves that by teaching AI to understand the logic of a scene, how things cluster, stack, and fit together, we can create much more effective and realistic training grounds for the next generation of robotics.